given a surface like this, we can calculate the tangent plane at a point in the surface. So the tangent plane is going to be given if we have that this point here is the point x0, y0, z0. So the equation of this plane is going to be given by this equation. Z minus the third component of the point, and then the values of the partial derivatives at x0, y0, meaning this part of the point, the two partial derivatives evaluated at x0, y0, and then multiply by x minus the x of the point and y minus the y of the point. So this will give us the equation of the tangent plane. As we have seen previously, have to calculate the equation of a plane by a point and the normal direction. So given the function that we want to calculate the tangent plane to, and given the point, so what we need to calculate the equation of the plane first is the derivatives and then evaluate them at the point. So let's do this in an example. So let's consider the surface given by this function x squared plus 3y squared, and we want to calculate the tangent plane to that surface at this point, 3 to 21. So in order to do that, we are going to first calculate the partial derivatives of this function. The partial derivative with respect to x in general is going to be equal to, derivative with respect to x will be just 2x, and the derivative with respect to y of the same function is going to be just the derivative of this term, which is 6y. And then we need to evaluate, according with our formula, we need to evaluate the derivatives at the first components of the point. In this case, will be at 3, 2. So let's evaluate these derivatives at 3, 2, meaning 3 for x, 2 for y. So in this case, will be 6, and evaluate this as 3, 2 will be 6 times 2, which is 12. So we have the two numbers that we needed for the equation of the plane. So the equation is going to be, following this formula, z minus the last component, x minus y minus the two first components, and the two derivatives evaluated at the point that are the coefficients that we just calculated. So the equation is going to be then z minus 21 equals the first coefficient, which is 6, x minus 3 plus the other derivative evaluated at the point, y minus the second component, that will be 2. Okay, so this is the equation of the plane. We can do the operations here, distributive, and this will be z minus 21 equals and so putting everything else in the second side, we have that this will be 6x plus 12y, and so here we have minus 18 minus 24 plus 21, so the final answer here will be minus 21 there. Okay, so this is then the equation of the plane tangent to this surface at this point. Using that tangent plane, we are going to define what is a linearization. Essentially, a linearization of the function is to calculate what is the plane that is closer to the surface. If we have a surface that is defined by some formula that may be complicated, like with exponential, logarithms, powers, not necessarily a plane. The plane is the simplest of the formula, will be linear, will be everything degree 1. we can calculate what is the plane that beta approximates this surface. So then we will have an approximation to the surface by a plane, meaning an approximation to a complicated function by a very simple function that has all exponents 1. And the linearization is very familiar if you remember the linearization for functions of one variable. So the linear function in two variables now is going to be equal to the function evaluated at the point plus the derivative at the point times x minus a, the other derivative, the other partial derivative at the point times y minus b. So remember that these things are evaluated, so all these three things are just numbers. So what you are going to get here is really a linear function, I mean depending only on the variable x and y with exponents 1. So there's not going to be an exponential, a logarithm, and a higher power. Let's calculate what will be the linearization, considering that we have everything calculated already, right? So we have the derivatives at the point, we have how much is the function at the point. So let's calculate them, the linearization. We have already that f at 3, 2 is equal to 21, the first derivative at 3, 2 was equal to 6, and the second derivative at 3, 2 was equal to 12. We have calculated that before. So then the linearization of this surface is going to be equal to the function evaluated at the point, is just 21, plus the first derivative, which is 6, x minus 3, and the second derivative, which is 12, y minus 2. So doing the operations here, we get that the linearization of this function is 21 plus 6x minus 18. And simplifying here, we get that the linearization is 6x plus 12y. This is the linearization of the function, which is nothing but the tangent plane, right, that we have calculated before. That's what linearization is. Essentially, linearization is the answer to the question, what is the plane that is closer to the surface at that point? So observe that because this plane is closer to the surface, we can use it to calculate values in the surface. I mean, they are not going to be exact, except for this point that will be exactly the same. All the points around here, let's say in a disk around here, they are not going to be exactly the same, but they are going to be very approximated. If you take points far away, for instance here, so then the value in the plane and the value in the surface may be far away. But around the point where we are calculating this, in this case the point 3, 2, around 3, 2, we can use this linearization to calculate the values of a more complicated function. So let's do a complete example of this. I mean, how would you calculate an approximation having the equation of the plane, essentially? Well, so in this case, we want to calculate f evaluated at 1.1, 2.1, and the function is this one. Of course, we could just plug in the function and find out how much is this. But this function have a cube, have a square, or sometimes the function have a logarithm, an exponential. So then, in order to simplify the plugging in, the evaluation, instead of plugging in the actual function, we are going to calculate the plane that is close to the function, and then we are going to plug in the plane, that the operations are going to be much simpler than in the function. So let's start by calculating then the equation of the plane. We start by calculating the partial derivatives. Derivative with respect to x will be 3 times 2 will be 6 x squared minus y. The derivative with respect to y is going to be minus x plus 2y. Okay, so now we have the function, the derivative respect to x and the derivative respect to y. We need to evaluate all these three functions at the point, but at what point? So observe that we want to calculate the value at 1.1 and 2.1. Well, we have to think this is a point that is close to what? Well, it looks close to 1, 2, right? So 1, 2 is the point around where we want to do the approximation of the surface by a plane. Exactly at one point they are going to coincide, but at a point that is close to it, like this one, which is 1.1, 2.1, they are not going to be exactly the same, but they are going to be very close. That's what it means to approximate the function by the value in the linearization. Okay, so in that way we choose that the point that we're talking about is going to be the point 1, 2. And then we evaluate now all these three functions at 1, 2. So the first one, f at 1, 2 is going to be equal to 2 minus 2 plus 4, which is 4. The first derivative at 1, 2 is going to be 6 minus 2, which is 4. And the derivative, the derivative respect to y at 1, 2 is going to be, substituting here, minus 1 plus 4, which is 3. So we have the three numbers that we need in the linearization. So the linearization is going to be equal to 4 plus 4 times x minus 1 plus 3y minus 2. So doing these operations here, doing distributive here, multiplying here, we get the linearization is 4x plus 3y minus 6. So what we have here is that our function is approximately the same that this one. So observe that this one is linear, the exponents are all ones, instead this one has cube and is more complicated. Okay, so let's just write down that. So our function f of x is going to be approximately equal, not equal, but approximately equal to the linearization, right, to Lx, y. And so instead of plugging in the function, we are going to plug in the linearization, and we are going to obtain an approximated value to the function. So let's do that. Let's evaluate now at this point 1.1 and 2.1. 1.1, comma 2.1. This is going to be equal to 4 times 1.1 is 4.4 plus 3 times 2.1 will be 6.3 and minus 6. So doing the operations here, 6 and 4 is 10.7 minus 6, and this is going to be equal to 4.7. Observe that if you actually plugging in the function directly the values 1.1 and 2.1, you will not get exactly 4.7, but you will get something that is very close. So this is then to approximate a function using the tangent plane or the linear approximation. We are going to call then just the function linearization, or we are going to call also linear approximation when we approximate the function by Lxy, which is all this. So we said before that the function is approximately equal to the linearization, but are not exactly equal. The difference between the two is what is called the error. So f of xy minus the linearization is what is called the error at the point xy. So what we want is this error to be very small. So we are going to say that function is differentiable if the two partial derivatives exist, and when you write here the error, that's what it is, this one, right? The difference between the function and the linearization. So the error divided this norm here. The limit of this when xy approaches to AB should be 0. I mean, when we are very close to the point, so this limit should be equal to 0. So this is the definition of the differentiation, though there is a theorem that allows us to decide more easily if a function is differentiable or not. So this theorem says that if both partial derivatives exist in a neighborhood of the point and are continuous at AB, so then the function is differentiable. And in that case, we're going to say that the total differential of the function is dz equals the first partial derivative, dx, plus the partial derivative respect to y, dy. So for example, let's calculate the total differential of this function. That was the same one that we had calculated before. So we know already that the derivative respect to x is going to be equal to 6x squared minus y, and the derivative respect to y was minus x plus 2y. So then the total, these two functions are continuous, right? So both are polynomials, so these functions are continuous, so this function is going to be differentiable. And the differential is going to be equal to the first derivative respect to x, 6x squared minus y dx, plus the derivative respect to y, which is minus x plus 2y dy. So this is the differential, the total differential of this function.